Welcome to Direct Preference Optimization, DPO. This tutorial explains how to align language models with human preferences without traditional reinforcement learning. Unlike RLHF, which requires training a reward model and running an RL optimization stage, DPO learns the policy directly from preference data, eliminating both explicit reward modeling and RL. Let's begin with maximum likelihood estimation, a fundamental principle in machine learning. Imagine you have some observed data points, shown here as circles on our plane. You want to find the best model parameters that explain this data. MLE answers the question, which parameter theta makes our observed data most probable? The answer is at the peak of this likelihood curve, where the probability of observing our data is maximized. Mathematically, if we have data points and a model with parameters theta, MLE finds the theta that maximizes the probability of observing our data. We write this as argmax of the product of probabilities for each data point. Here we see 3 data points, each with its own probability given theta. MLE multiplies these probabilities together and finds the theta that makes this product as large as possible. In practice, we work with log likelihood instead of raw likelihood, because probabilities are tiny numbers that, when multiplied together, can cause numerical underflow in computers. Multiplying 0.001 times 0.002 times 0.003 creates numerical instability. Taking the logarithm converts products into sums, which are much more stable to compute with manageable negative numbers. Here's a key insight. Maximizing log likelihood is equivalent to minimizing negative log likelihood. The left plane shows maximizing log L, while the right shows minimizing negative log L. These are mathematically equivalent operations. This is why loss functions in machine learning are often defined as negative log likelihood. It connects naturally to gradient descent, where we minimize loss functions by following the gradient downward to find the optimal parameters. Now let's explore the Bradley-Terry model, which is fundamental to understanding preferences. Imagine you have 2 text completions from a language model, shown here as y_1 and y_2. A human evaluator tells you they prefer completion y_1 over completion y_2. How do we model this preference mathematically? Each completion has an associated reward value, r of y_1 and r of y_2. The Bradley-Terry model gives us a principled way to convert these rewards into preference probabilities. The Bradley-Terry model says the probability of preferring completion 1 over completion 2 depends on the rewards through this formula. The probability equals e to the power of r of y_1 divided by e to the power of r of y_1 plus e to the power of r of y_2. Visually, we exponentiate each reward to get these bars. The probability is the ratio of the left bar's height to the total height of both bars combined. Here's the crucial insight. This probability depends only on the difference between rewards, not their absolute values. We can rewrite the Bradley-Terry formula using the sigmoid function. The probability of preferring y_1 over y_2 equals sigmoid of r of y_1 minus r of y_2. This sigmoid curve shows how the preference probability changes with the reward difference. When the difference is 0, the probability is 50%. When y_1 has higher reward, the probability increases. When y_2 has higher reward, the probability decreases. Only the difference matters. What does this mean intuitively? Look at these 2 scenarios. On the left, y_1 has reward 5 and y_2 has reward 3, giving a difference of 2. On the right, we've added 5 to both rewards. y_1 now has reward 10 and y_2 has reward 8. The difference is still 2. Because the Bradley-Terry model depends only on the difference, both scenarios give exactly the same preference probability, sigma of 2. This property becomes crucial in DPO because it means we only need to model reward differences, not absolute reward values. Let's discuss KL divergence constraints, which are essential in reinforcement learning from human feedback. When we fine-tune a language model, we face a critical challenge. We want to improve the model according to human preferences, represented by moving from the reference policy on the left to a learned policy on the right. But we don't want the learned policy to deviate too far from the reference policy's original behavior. The KL divergence measures this deviation, and we constrain it to stay within bounds shown by this boundary box. Without this constraint, several problems arise. First, the model might exploit weaknesses in the reward model by generating nonsensical text that happens to score high rewards. This is called reward hacking. Second, it might forget the broad capabilities it learned during pre-training, a phenomenon called catastrophic forgetting. Third, it might become over-specialized on the preference task, losing its general language understanding. The KL constraint acts as a protective barrier, preventing these pathological behaviors by keeping the model tethered to its pre-trained knowledge. The KL constraint acts like a regularizer, keeping the new policy tethered to the reference policy while still allowing improvement. Mathematically, we optimize the expected reward minus beta times the KL divergence between pi and pi reference. Beta controls how strictly we enforce staying close. The blue curve shows expected reward increasing as we move away from the reference. The red curve shows the KL penalty decreasing as we deviate more. The green curve shows their sum, which has a clear maximum. This optimal point balances reward improvement against staying close to the reference policy. Now we arrive at a beautiful mathematical relationship in KL-constrained reinforcement learning. When we solve the optimization problem of maximizing expected reward while keeping KL divergence bounded, the optimal policy has a specific, elegant form. The optimal policy is proportional to the reference policy times the exponential of the reward divided by beta. Visually, we start with the reference policy, multiply it by this exponential weighting factor based on the reward, and get the optimal policy. Completions with higher rewards get exponentially amplified. Notice that this formula includes a normalization term called the partition function, z of x. This partition function is the sum over all possible completions, y of pi reference, times exponential of reward divided by beta. We see 5 example completions here, but in reality, we must sum over all possible text completions. This is what makes traditional RLHF computationally challenging. The space of possible completions is astronomically large, making this sum intractable to compute exactly. Here's DPO's key innovation. We can rearrange this formula to express the reward in terms of the policy. Starting with the optimal policy formula, we multiply both sides by z of x. Then we divide by pi reference. Then we take the log of both sides. Finally, we multiply by beta to isolate r. The result is reward equals beta times log of pi over pi reference plus beta times log z of x. This rearrangement is the foundation of DPO's elegance. This change of variables is profound. Traditional RLHF, shown at the top, requires learning a reward model, then computing the intractable partition function z of x, then running RL optimization to get the final policy. The partition function computation is the bottleneck. DPO, shown at the bottom, takes a different approach. We directly parameterize the policy and work with an implicit reward. Here's the magic. When we substitute this reparameterized reward into the Bradley-Terry preference model, the partition functions cancel out. We never need to compute z of x, making the entire process tractable. DPO introduces the concept of an implicit reward model defined directly in terms of the policy being learned and the reference policy. The implicit reward has this elegant form: r of x, y equals beta times log of pi theta of y given x divided by pi reference of y given x. Let's break this down visually. We start with 2 probabilities, the learned policy's probability and the reference policy's probability. We take their ratio. Then we take the logarithm of this ratio. Finally, we multiply by beta. This gives us the implicit reward without ever training a separate reward model. This formula says the reward is proportional to the log ratio of the learned policy to the reference policy. Let's interpret this. When the learned policy assigns higher probability to a completion than the reference does, the ratio is greater than 1, the log is positive, and the reward is positive. When the learned policy assigns lower probability, the ratio is less than 1, the log is negative, and the reward is negative. When both policies agree, the ratio is 1, the log is 0, and the reward is 0. The implicit reward naturally captures how much the learned policy prefers each completion relative to the reference. Now we arrive at DPO's brilliant connection. Learning from preferences can be reformulated as a binary classification problem. Given a pair of completions where y_w is the preferred or, winning, completion, and y_l is the dispreferred or, losing, completion, we want to maximize the probability that our model assigns higher reward to y_w. This is exactly like binary classification. We want to correctly classify which completion is preferred. We maximize the implicit reward of the preferred completion and minimize the implicit reward of the dispreferred one. Using the Bradley-Terry model with the implicit reward, the probability of preferring y_w over y_l has this form. It's the sigmoid of beta times log pi, theta of y_w over pi, reference of y_w, minus beta times log pi, theta of y_l, over pi, reference of y_l. Let's break this down. For y_w, we compute the log ratio of the learned policy to the reference policy. For y_l, we compute the same log ratio. We subtract the y_l term from the y_w term. Finally, we pass this difference through the sigmoid function to get a probability between 0 and 1. Maximizing the likelihood of observed preferences under this model is equivalent to minimizing a binary cross-entropy loss. The DPO loss function is the negative expected value of log sigmoid of the implicit reward difference. This is exactly the negative log likelihood of the preference data. We've seen this pattern before. Maximizing likelihood is equivalent to minimizing negative log likelihood. Here, we're maximizing the likelihood that our model correctly predicts human preferences, which is the same as minimizing this cross-entropy loss. It's standard supervised learning. The beauty of this formulation is that this loss can be optimized using standard supervised learning techniques. No reinforcement learning required. Here's the complete training procedure. We start with a preference dataset containing tuples of prompt X, preferred completion y_w, and dispreferred completion y_l. We treat each preference pair as a binary classification example. We compute the DPO loss for each pair. We use gradient descent to adjust the policy parameters theta to minimize this loss, which increases the probability of correct preferences. It's that simple. No reward model training, no RL algorithms, no complex optimization, just straightforward supervised learning. Let's synthesize everything into direct preference optimization. The key insight is the reparameterization. By expressing the reward as beta times log pi over pi reference plus beta times log z of x and substituting into the Bradley-Terry model, the partition functions cancel. Watch carefully. We substitute the reward formula into the preference probability. We get r of y_w minus r of y_l. When we expand this, we see beta log z of x appears in both the y_w term and the y_l term. When we subtract them, these partition function terms cancel out completely. We're left with only the policy ratio terms. This cancellation is the mathematical heart of DPO. DPO streamlines the traditional two-stage RLHF pipeline into a single unified training stage by directly optimizing the policy from preference data. This approach removes the need for an explicit reward model and the reinforcement learning loop, making training simpler to implement, more stable by avoiding RL-specific instabilities, and more computationally efficient due to reduced overhead. The DPO loss gradient has a dynamic importance weight based on ranking errors. Its magnitude is the sigmoid of minus beta times the reward difference. Large when the model prefers y_L over y_W, strong correction, medium when uncertain, and small when it correctly prefers y_W, minor adjustment. Specifically, the gradient raises the likelihood of preferred completions and lowers that of dispreferred ones, with update size weighted by the sigmoid of minus beta times the reward difference. When the model correctly scores y_W much higher than y_L, 5 versus 1, the sigmoid is near 0, so updates are small. When it incorrectly scores y_W lower than y_L, 1 versus 5, the sigmoid is near 1, producing large corrective updates. Direct preference optimization aligns language models with human preferences like RLHF, but in one step. By reparameterizing rewards, it cancels out complex computations and turns preference learning into simple binary classification. No separate reward model or RL is needed. Training is stable, efficient, and theoretically sound.